Welcome. So I just want to make a quick video about some basics of problem solving. So two key things I want to talk about are the four-step problem solving process and how to solve problems using various problem solving techniques. So the four-step problem solving process, this comes from Koya. It's a very classic process. And it's actually pretty abstract. The four steps are: one, understanding the problem; two, devising a plan; three, carrying out the plan; then four, looking back. Now, here's the key thing. This process, while it does seem algorithmic, it has numbers and steps. There's a lot of different ways you can do this. How do you understand the problem? How do you devise a plan? How do you carry out that plan? And how do you look back on it? So let's talk about that real quick. So how to understand the problem? Well, the first thing is, can the problem be stated differently? In other words, think about it for a second. Can I rewrite this and state this a little bit different? What is to be found and what is needed? In other words, what am I looking for? And that's what I always like, those keywords. What are the things that I don't know? Also, as you read through it, what are the things that you do know? What information is being given to me? Also, what is missing? So some of these are really connected. Some of the unknowns are the missing information. Sometimes we need information before we can progress forward. There's a formula. I just don't know something. These are good questions actually for general problems. We do this in life all the time. Like facing a challenge, I have to ask myself these questions. Then we need to devise a plan. So we have all these key things. Then we go to devising a plan, which these are a bunch of different plans that are possible. One, we can simply look for a pattern. So, if something keeps happening after something else, if let's say event A always happens after event B, so my kid always gets sick after I give them popcorn, well, that's a pattern, okay? Examine related problems. So even in math, we ask, is this very the same? Sometimes I think the problem is we get too comfortable. We think that everything is exactly the same technique, and that doesn't always work. Now, I like step C, which is examine a simpler or special case to gain insight. So sometimes when I'm trying to solve a problem, I just look at something very simple about it. I look at a specific subset. What would happen if I restricted to this? That's actually how I do a lot of my different work to move forward and kind of explore different concepts. Then we need to, another strategy is to make a table or list. Start looking at, can I list things out and see a path? Again, sometimes making the tables helps you see those lists. Sometimes you want to make a sub goal. I can't solve this whole problem, but let me figure out this, and then maybe I can get to that second part. And then we can make a diagram, we can draw pictures. Guess and check is actually a viable thing. I can guess this is, but how do I check it? Now, there is pros and cons of all these. Working backwards, writing an equation. You don't have to write an equation for every problem. So we do have all these strategies. So which one do I use? You need to pick it pretty much based on what do you understand about that problem. Then I have to go to how to carry out that plan. So depending on which of these strategies, I may pick two of them. But depending on which one I picked, how I perform that and then perform necessary steps. And then I need to pay attention to language, the mathematics, the technical, because these are the technical things. And each step along that plan. So for instance, if I'm looking for a pattern, okay, let me look at several key things in this pattern. What can I interpret from that? From working backwards, okay, well, I'm here. That leads me back to this step, which leads me back. You have to take it step by step. You can't just jump through it. You have to apply all those different things. And that's a really key thing. Even when I gave you and I a very simple mathematical problem, your brain is doing something in your head. So if I asked you to do, for instance, what is 43 times 15? If I asked you to do that in your head, you would still do steps. You might only iterate what you ended up with, but the process is actually how to do it. So this is that carrying out the steps. And recording accurate work is important. So while we often encourage to do certain things in our heads, writing it down is really, really critical. And that's going to come up over and over again in this class. Then finally, we want to look back. We want to interpret our solution. Does it make sense? Were there other methods that we could have used? Maybe were there other solutions that are possibly out there? Does this even actually work? Like, for instance, if I'm dealing with the problem of time, trying to find some amount of time, I get a negative answer that probably doesn't make sense unless I have a flux capacitor. So I'm probably gonna have to deal with some different things. So let me show you all of this. So these strategies for problem solving are just simply tools. Imagine this as a giant tool chest. One tool does not always work. Does a hammer work for a lot of things? Yeah, it does. But does it work for everything? Not necessarily. So because of that, a problem can be solved in usually more than one way. So there is not one best strategy. There's not, this is the best. This strategy might be more effective than other. Again, what are the strengths and weaknesses? So let's just give you an example. So I'm going to give you, this is a problem that's a little bit of a story. We actually don't know if this did occur, but a lot of things suggest it did. So Carl Gauss is a very famous mathematician. When he was a child, some project in his elementary school days, his teacher required all the students to find the sum of the first 100 numbers. So that's 1, 2, 3, all the way up to 100. Now, as the story goes, and this problem is written very simply, but the teacher simply wanted some free time. I mean, honestly, if you hand it to a kid, it's going to take them a long time, right? To add those up. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 5 plus 10 is 15. It's just keep going on from there. The teacher expected this problem to take the class a while. That way they'd have free time. But Gauss figured out this answer almost immediately, and he was kind of surprised. And so how did he do it? What he did was he looked for a pattern. So he looked at the numbers, 1, 2, 3, 4. And the problem was asking to add these up. So what he then said was, what if I took the numbers, so 1, 2, 3, 4, 5, 6, 7, let me get my little fancy wand so I can point this out to you. So see, he has all the numbers, and then he added them in reverse. Because we know that adding doesn't matter the order in which you do it. So, but notice, what's 1 plus 100? It's 101. What's 2 plus 99? It's 101. 3 plus 98 is 101. Hey, wait a minute, all these are 101s. And in addition to that, one of the things that we happen to know, I'm just going to write this down real quick, is that there are 100 of these numbers. Because we know that each one, this is 1, 2, there's 100 numbers across, and when I add them together, we get 101. So if I add the same sum within itself, I get 101 added together 100 times. Well, we know that from multiplication, that this will give us 2 times our sum, or in other words, whatever our number is by 2, but we also know that that's 100 times 101 is 2 times, so I just divide everything by 2, and this multiplication right here is actually pretty easy. Even easier when you do 100 divided by 2, well, that's going to be 50. And then multiply 50 times 101 is 50 times this would be 50 times the 1 would be another 50. So that's why it's 50-50. 5,050, if you prefer to say it that way, it's all the exact same idea. So he came up with this idea by simply seeing a pattern that if I add them in reverse, I get the same exact number over and over again. So Gauss saw this, and now let's look back. If it's performed actually correctly, so you don't make arithmetic mistakes, you can see this pattern, and you can see that repeating addition is the same thing as multiplying something by 2. In addition to that, each sum adds up to 101 because when we move it from one pair to the next, we add 1 to one number, subtract 1 from the bottom, which does not change the overall value. Because if I start with 1, the next number would be 2. Well, that's 1 more than 1, and 100 goes down to 99. That's why we balance it out. This idea of simply manipulating numbers is often a common thing that we do, which is why students, your students, need to be comfortable with it. But you can't teach them that if you're not comfortable. So be willing to kind of play with these numbers, massage them, be comfortable with them. They're not scary. I promise they won't bite. All right, so this idea we can repeat over and over. One of your assignments this week is actually to try to come up with a different way to find this besides this pattern we just saw. So besides this repeated backwards addition, is there a different way to have found the same sum? You now know the answer. Can you work it out differently? All right, that's to get you started on problem solving. Come back and watch my other video on problem solving where I do a logic problem for you.